West Sea in February runs gray and cold under a sky that rarely differentiates itself from the water beneath it. The color is the same in both directions, a flat, pewter gray that absorbs light rather than reflecting it, and on overcast days makes the horizon line a matter of estimation rather than observation. Water temperature at the surface is 3 degrees Celsius. Air temperature is -6. The prevailing wind from the northwest drives a short, steep chop across the shallow basin. The West Sea averages 38 meters depth across the patrol corridors near the northern limit line, which means the wave energy has less water column to dissipate into, and the resulting sea state is more aggressive than the wave height alone would suggest. A ship in this environment works harder than the weather report implies. USS Fitzgerald makes 14 knots on a southerly heading, 41 nautical miles south of the northern limit line. She has been conducting coordinated presence operations with ROK naval forces for 6 days, and the exercise concluded 22 hours ago. She's now in transit toward Busan, running at reduced watch bill with the post-exercise crew settling into the transit routine. The ship is not at general quarters. She's at modified readiness, an intermediate posture that places one watch section at elevated alert, while the remainder of the crew maintains the ship in standard transit configuration. It is 11:47 p.m. The EM-11 influence mine was laid by a North Korean submarine at an undetermined point in the past 14 to 21 days. The West Sea mine threat is not theoretical. North Korea maintains an active mine warfare capability, and the shallow bathymetry of the West Sea makes influence mines effective in ways that deeper water does not. The mine sits in 22 meters of water, anchored 3 meters off the bottom, with its magnetic and acoustic influence sensors in an active monitoring state. It has been monitoring passing vessels for days. The Fitzgerald's magnetic and acoustic signature matches. The EM-11 detonates beneath the keel at 11:47:33 p.m., centered approximately 14 meters forward of amidships, at a standoff depth of approximately 8 meters from the hull. The 320-kilogram warhead generates a gas bubble in the shallow water column that oscillates twice before venting to the surface, a phenomenon specific to shallow water mine detonations that distributes the hull loading differently from a deep water event. The bubble pulse loading arrives at the keel as a distributed upward impulse followed immediately by a downward suction pulse as the bubble collapses. The combined loading applies a vertical whipping motion to the hull. The bow and stern deflect upward while the midship section deflects downward. Then the pattern reverses at a frequency determined by the hull's natural bending mode. The Fitzgerald undergoes 2 complete whipping cycles in 1.4 seconds before the hull dynamics damp out. In those 1.4 seconds, the hull bends. The amount of bending is small, measured in millimeters of midship deflection, well within the structural design envelope. But every pipe, every bracket, every fitting in the ship experiences the bending load simultaneously. And the weakest points in the ship's piping architecture experience the highest fraction of the design load. 3 of those points fail. The first failure point is gas turbine generator number 1's vibration isolation mount. The whipping load exceeds the mount's transient design limit, and the GTG trips on its vibration sensor 11 seconds after the detonation. GTG number 2 trips simultaneously. Its mount fails in the same whipping cycle. The forward main switchboard loses the 2 generators feeding it and sheds its load. In CIC, the tactical displays go dark. The SPY-1D radar stops mid-sweep. In the forward passageway, the white lighting shifts to emergency red. The second failure point is a 4-inch Firemain riser elbow at frame 41, port side, where the vertical riser transitions to the horizontal distribution header on the second deck. The weld at this elbow has been in service for 11 years. The whipping load applies a bending moment to the elbow that the weld resists and then does not resist. The weld cracks along its fusion line in the 0.3-second downward suction phase of the second bubble pulse. When the hull bends in the opposite direction and the elbow fitting is loaded in tension rather than compression, the crack propagates through the full weld cross-section in 0.2 seconds. The elbow separates. At 90 pounds per square inch operating pressure, the 4-inch Firemain riser now has an open end at the frame 41 elbow joint, and the water that comes out of it does not go to firefighting hoses. It goes to the second deck of the ship at 380 gallons per minute. The third failure point is a cable conduit penetration seal at frame 43, starboard side, where a bundle of electrical cables passes through the watertight boundary between the second deck and the forward electrical trunk. The penetration seal is a rubber compression fitting. The whipping load has deformed the seal housing by 1.1 millimeters, not enough to rupture the seal, but enough to break the compression fit and allow moisture to begin tracking along the cable insulation into the electrical trunk below. At 11:47:44 p.m., 11 seconds after the detonation, the crew of USS Fitzgerald is managing the following: a ship with no forward electrical power, no primary radar, no fire control capability, a forward flooding situation producing 380 gallons per minute on the second deck from the separated Firemain riser, and a moisture ingress in the forward electrical trunk that has not yet manifested as a fault but will. The general alarm sounds on emergency diesel power at 11:47:51 p.m. The flooding alarm for the second deck, frame 38 to 44 space, activates at 11:48 and 9 seconds p.m. as the water level from the Firemain discharge reaches the flood sensor threshold. The watch officer in DC Central reads this alarm and misidentifies it for 12 seconds. In a mine detonation scenario, the expected flooding source is a hull breach, water coming in from outside through damaged plating. The second deck, frame 38 to 44, is 3 decks above the waterline. Water on the second deck is not the expected reading. The watch officer pulls the DC display for that frame range and sees no hull breach indicators. The flooding source is internal. His hand goes to the sound-powered phone at 11:48:21 p.m. and by 11:48:30 p.m., the chief engineer has the assessment. The forward Firemain is feeding the ship's own interior. This is the specific catastrophe that the chief engineer has considered in the abstract during training exercises and has not previously encountered in operational service. The Firemain system, the ship's primary firefighting infrastructure, 90 pounds per square inch of seawater running through a ship-wide pipe network designed to put water on any fire aboard within 30 seconds of a hose connection, has become the source of the flooding. The system designed to save the ship from fire is now threatening to flood it. And the only way to stop it is to shut the Firemain down entirely. Shutting the Firemain down entirely means the ship has no firefighting water. No water means no hose station capability, no foam application, no suppression system that relies on Firemain pressure. On a ship with an active electrical system that has just taken a mine shock and has moisture tracking into an electrical trunk, having no firefighting water is not a theoretical problem. It is a ticking sequence. The electrical fault from the penetration seal moisture will arrive as a short circuit. Short circuits on a ship with JP5 fuel in the lines and hydraulic fluid in the machinery spaces generate ignition energy. A fire with no water available to fight it is an uncontrolled fire. The chief engineer has this picture in his mind. At 11:48:30 p.m., he is standing in DC Central with a sound-powered phone in his hand and the status board showing 2 GTGs offline, a second deck flooding alarm active, and a forward electrical trunk moisture alert transitioning from amber to red on the panel. As the cable insulation tracking produces a fault on a 440-volt distribution circuit, he calls the repair party 1 leader. Frame 41, port side, second deck. The Firemain riser elbow has separated. You will find a 4-inch open pipe dumping on the second deck. I need that riser isolated at the frame 40 isolation valve above the brake and at the frame, 44 distribution valve below it. Once isolated, you will have no fire main pressure in the frame 38 to 44 zone. Be aware. Simultaneously, post fire watch on the forward electrical trunk at frame 43 starboard because I have a fault on circuit J14 that is going to become a fire without water, and I am working the alternatives. Move now. He calls the engineering watch. Forward main switchboard space. I need a visual on the starboard penetration seal at frame 43. I need to know if there is physical moisture on the cable bundle, and I need to know before that fault becomes a trip on the main bus. He picks up the 1MC. All hands, damage control. Forward fire main isolated. No water pressure in the forward hose stations. Frames 1 through 50. Fire watch teams, man forward positions. Alternative suppression only. DC Central is coordinating alternative water sources. He has isolated the fire main. He has announced it to the ship. He has told his crew they are fighting any forward fire without water pressure. He now has an estimated 12 minutes. Based on the fault propagation rate he is watching on the distribution system monitor, to provide them with an alternative before the J14 fault becomes a fire. The alternative is the ship's P250 portable pump inventory. The Fitzgerald carries 2 P250 portable pumps in the forward damage control locker that can be connected to the overboard seawater suction and used to deliver water to a fire through a 1.5-inch fire hose. Not at 90 psi fire main pressure, but at 35 to 40 psi, which is sufficient for a fire that is not in a fully involved fuel-fed space. Getting a P250 pump deployed to the forward electrical trunk at frame 43 takes 4 minutes from the locker to connection. He has 12 minutes. He has an 8-minute buffer. He calls the damage control locker watch. Get a P250 to frame 43, starboard electrical trunk, port access. I want water on that space in 4 minutes. Then he goes to the flooding. Repair Party 1 has reached the second deck at frame 41. By the time the chief engineer arrives at 11:49 and 12 seconds p.m., the space looks wrong in the way that no training exercise ever quite replicates. The emergency red lighting turns the water on the deck surface into dark pools that reflect the overhead light sources. And the sound of the fire main discharge, a sustained, high-pressure roar coming from the separated elbow 4 feet above the deck, is loud enough to require hand signals between team members rather than voice commands. The water is at 6 inches and rising. The frame 38 to frame 44 space has no overboard drain path at the second deck level, so the water is pooling. The frame 40 isolation valve is on the port side of the space, above head height, accessible from a step ladder. The valve wheel is a 10-inch diameter hand wheel, operated by rotating clockwise to close. The chief machinist's mate reaches the valve at 11:49:38 p.m., places both hands on the wheel, and turns. The valve has been power operated for its service life and responds to hand operation with the resistance of something that has never been asked to do this before. He puts his full body weight into it, both hands on the wheel, and the valve turns, slowly, requiring 8 full revolutions from fully open to fully closed. He completes the first revolution. The discharge rate from the separated elbow drops by approximately 15%. Second revolution. The roar in the space drops in pitch. Third revolution. The pooled water on the deck has reached 8 inches. The valve takes 4 minutes and 7 seconds to fully close. 2 people working it in rotation because the stem resistance increases as it approaches the closed seat, and neither person can maintain the required torque for more than 90 seconds at a time. The second person is a damage controlman who has never operated a manual fire main isolation valve in service conditions. He is aware of this. He is also aware that the water is at his shins and rising. He operates the valve. At 11:53:45 p.m., the frame 40 isolation valve reaches its closed seat. The discharge from the separated elbow drops from a roaring pressure discharge to a low pressure dribble as the residual pressure in the isolated section bleeds off. The flooding stops. The water on the second deck is at 11 inches, at the point where it would have reached the electrical conduit runs and threatened the distribution panels at frame 44. It has not reached them. The pooling will be dewatered by P250 pump. The frame 44 distribution valve, below the brake, has been closed simultaneously by the second element of repair party 1. A 2-minute procedure on a valve that closes faster than the frame 40 valve. The forward Firemain zone from frame 1 to frame 50 is now dry, isolated, and incapable of fighting fires. At 11:57 p.m., while the frame 40 valve was still being operated. The circuit J14 fault in the forward electrical trunk produced the short circuit the chief engineer had predicted. The arc from the fault was brief. The main breaker tripped within 0.3 seconds. But it was sufficient to ignite the cable insulation on the affected cable bundle. Cable insulation fire is a low-intensity but persistent fire that produces dense acrylic smoke and will reignite repeatedly if not fully extinguished because the insulation material continues to smolder after visible flame is suppressed. The fire started in the forward electrical trunk at frame 43 at 11:57 p.m. The fire watch team posted by the chief engineer at 11:48:30 p.m., 47 seconds before the fire started, saw the arc and the initial flame. The P250 pump reached the frame 43 access point at 11:51:52 p.m., 1 minute and 35 seconds after the fire started. 2 minutes and 8 seconds from the chief engineer's call to the DC locker. The pump delivers water at 38 pounds per square inch through a 1.5-inch line. Cable insulation fires do not respond to water the way open flame fires do. Water suppresses the visible flame, but the smoldering continues, and the fire watch team has to trace the burn path along the cable bundle and apply water to each section of affected insulation systematically. This takes 9 minutes and 30 seconds of sustained application. The team finds 2 sections that reignite after initial suppression, traces each to a residual heat source in the bundle, and applies water to the thermal source rather than the visible smoke. At 12:01:27 a.m., the fire in the forward electrical trunk is confirmed out. The space is smoked and wet. The cable bundle at frame 43 will require full replacement. The arc fault and fire damage have compromised the electrical integrity of every cable in the affected bundle, which includes the primary power feed for the forward DC-DC converters serving the SPY-1D radar auxiliary systems. The radar remains offline on 2 counts. The forward main switchboard fault from the GTG trips, and now the auxiliary system power loss from the cable bundle damage. The GTG restart effort has been running in parallel via sound-powered phone from DC Central since 11:48 p.m. The restart sequence for both generators requires the forward main switchboard fault to be cleared first. The switchboard fault cannot be cleared while the J14 fault is live. The J14 fault will not clear until the fire is out and the fault circuit is isolated. The sequence is fire out, then J14 isolated, then switchboard fault cleared, then GTG restart, then forward bus energized. The fire is out at 12:01:27 a.m. The J14 circuit is isolated at 12:03:11 a.m. by the electronics technician, who physically disconnects the affected cable bundle at both ends and installs a temporary bypass for the unaffected circuits. The switchboard fault clears at 12:04:08 a.m. GTG number 1 restarts at 12:05:44 a.m. The forward main switchboard accepts load at 12:06:17 a.m. The SPY-1D radar auxiliary power remains offline. The J14 cable bundle damage has taken out the auxiliary feeds, and those require physical cable replacement. The systems officer has identified a partial workaround. The radar can operate in a reduced power mode using only its primary feeds, without the auxiliary conversion system the J14 bundle was serving. Reduced power mode gives the SPY-1D approximately 60% of its normal transmit power. Enough for surveillance and track maintenance, not enough for fire control quality tracking. The ship can see. It cannot engage precisely. The radar comes up in reduced power mode at 12:09:41 a.m. The tactical display in CIC, dark since 11:47 p.m., reactivates. The watch team begins rebuilding the surface picture. The West Sea around USS Fitzgerald is empty of contacts, except for the ROK patrol vessel that has been responding to the detonation event and is now 14 miles to the north, approaching on a rescue bearing. The ship has not lost buoyancy. She is stable. The Firemain is isolated forward of frame 50, giving the aft portions of the ship full firefighting capability and leaving the forward sections dependent on P250 pump deployment for any fire response until the riser can be repaired. The separated elbow at frame 41 will need a new elbow fitting and a weld repair. Work that cannot be done at sea with water in the system and cannot be done safely until the forward Firemain section is confirmed dry. The temporary repair that Repair Party 1 installs at 12:15 a.m. is a mechanical end cap on the separated elbow stub, driven home with a rubber mallet and sealed with a steel compression collar. Not a pressure repair, but sufficient to keep the separated end from reflooding the space if the isolation valves are briefly opened for pressure testing. The forward Firemain section remains isolated and dry. The second deck flooding, 11 inches of West Sea mixed with Firemain water and a small quantity of hydraulic fluid from a drain line knocked loose in the whipping event, is dewatered by two P250 pumps working in parallel. The space is dry at 12:19 a.m. The mine that caused all of this was never seen, never tracked, and was never going to be. EM11. Influence mines do not reveal themselves, and the West Sea mine situation is, as it has always been, a matter of probability rather than specific intelligence. The Fitzgerald had transited this corridor. The mine had been waiting. The timing was what it was. The crew had not been negligent. They had been in a place where this kind of thing is possible, and it became probable, and then it became actual. The difference between those three states of affairs was a 320-kilogram warhead that detonated 8 meters from the keel, a 4-inch elbow weld that had been in service for 11 years, and 47 seconds between the chief engineer's fire watch order and the fire starting. 47 seconds. That was the margin on the fire. Not the hull, not the propulsion, not the radar. The fire watch was posted 47 seconds before the fire started, and the P250 pump arrived 95 seconds after the fire started. And the fire was out in 9 minutes and 30 seconds. The Firemain was not there. The water was there anyway, because the chief engineer understood what the sequence was going to be before it had finished being a sequence. One EM11 influence mine detonated 8 meters below the keel, 14 meters forward of amidships. Hull whipping, 2 cycles at 1.4 seconds, 2 GTG trips simultaneously. 1 Firemain riser elbow separation at frame 41, flooding rate 380 gallons per minute onto the second deck. 1 cable penetration seal deformation at frame 43, moisture tracking J-14 circuit. Forward Firemain isolated at 11:53:45 p.m. Forward hose stations offline from frames 1 to 50. J-14 cable bundle fire ignited at 11:50:17 p.m. Fire watch posted 47 seconds before fire ignition. P250 pump on station 95 seconds after ignition. Fire out at 12:01:27 a.m. GTG number 1 restored at 12:05:44 a.m. SPY-1D in reduced power mode at 12:09:41 a.m. Second deck dry at 12:19 a.m. Forward Firemain section isolated with mechanical end cap. Ship status operational. The post-event report filed at Busan identified one decision as the single most consequential action of the event: isolating the Firemain before the fire started. while the flooding was still active, based on a projected fault progression rather than a confirmed fire. The chief engineer was asked to explain the reasoning. He said he had watched J-14 fault progressions and moisture intrusion events on various ships for 7 years, and J-14 faults go to arc in 11 to 14 minutes. He said he had 8 minutes of buffer at the point he made the call. He said the only way to have firefighting capability when the fire started was to post the watch before the fire started, not after. And the only way to post the watch at the right place was to know where the fire was going to be. He was asked if he was certain the fire would start at frame 43. He said he was not certain. He said he was confident. He was asked what the difference was. He said certainty is what you have after the event, and confidence is what you act on before it. He said if the fire had not started at frame 43, he would have looked like someone who was overly cautious. He said he was comfortable with that outcome. The fire started at frame 43. The watch was already there.